My name is Timur, and today we are going to cover advanced topics in using exabyte.io. This webinar is second in the series, and again, my name is Timur. You can contact me at any time at timur@exabyte.io with any questions after the webinar. But before we start, let's figure out what the goal of the seminar is. The seminar is to help users experienced in computational material science understand how to use exabyte.io to perform like regular modeling tasks. So something that they do today, how they can do that with exabyte in a better way. This is the second webinar in a monthly recurring series. We have had our first webinar 2 weeks ago that was focused on getting started with the exabyte platform, the very basic concepts. Today, we will assume that users already understand the basics and we'll go forward with more advanced topics. Every participant should be a registered exabyte.io user to be able to follow along and do the exercises as we go. Every participant will receive this presentation in a PDF format after we're done. The presentation contains links like this, links to documentation, to tutorials that users can follow on their own time after we're done. This webinar is also recorded and will be made available online. And most of the information we have in the presentation is available at docs.exabyte.io. So for today, we will focus on the following user story. We will assume that the webinar attendee, the user, is an experienced computational material scientist, familiar with tools like Quantum Espresso, VASP, or similar. So computational material scientists who have established way to do simulations, curious about the platform, and would like to understand how to migrate their established set of scripts and routines to exabyte platform. We'll also assume that the users understand the basics of Linux and Unix operating systems and would like to know how to migrate their knowledge to use exabyte platform. There are two options for migrating, and the first option is to entirely bypass the web interface. We see that many people would like to use the familiar command line interface when they first encounter exabyte.io platform. And it's entirely possible to do that. It's possible to access command line environment and reuse existing scripts or input files to run command line jobs. The second option is to adopt the exabyte.io approach and create material entities in the platform, create workflow entities, and then create jobs with material and workflow. And I will cover these two approaches today. Both of them have pros and cons. So the good side about the first approach is that it's very quick to start and it's familiar for command line users. The negative part of it is that that's usually error prone. We always have to modify the input files, and it's difficult to reuse any kinds of input files and share them. For the second approach within the exabyte platform, it's the opposite. It's difficult to start with because it requires a learning curve, but all the calculations, all the workflows are usable for multiple materials and easy to share and review. Okay, so here is our agenda for today. We'll focus first on alternative connection methods like secure shell, web terminal, remote desktop. We'll speak a little bit about the file system on the login node to which we connect through remote desktop or web terminal. And then we'll speak about materials and how we can migrate material information from an example PWSCF input. PWSCF is part of Quantum Espresso suite, and we'll use that as an example to understand how we can migrate the material information to the platform. Then we'll proceed with the workflows and understand how we can migrate the workflow logic and unit input information from PWSCF input to the platform. And finally, we'll speak about executing simulations, how we can run command line jobs using existing PWSCF input, and how we can use the web interface to do the same. Okay? All right, so before we start, if you'd like to follow along, then you should have access to the webinar account. For the people who are newly joining and are not yet users of Exabyte, we'll enable them after we're done. But this webinar account is meant for the webinar attendees to try this functionality, to follow along and do exactly what I will demonstrate. This account have advanced features enabled for it, like command line access, remote desktop, and such. During the webinar, to save time, we'll see recorded videos of this functionality, but users can follow along and click exactly the same spots and the same buttons as demonstrated in the videos. All right. Accessing the webinar account can be done by opening the right-hand sidebar. So clicking on your name in the right top corner, and then clicking on My Accounts, as I'm demonstrating here. You will see that webinar is part of your accounts, and if you click on the webinar itself, you'll start using the platform as the webinar account member. Okay. All right, so let's proceed to the general concepts. First of all, to be able to understand the alternative ways to connect to the Exabyte platform, we have to first speak about the platform architecture a little bit and understand how it's designed. So here is a diagram that demonstrates different components. We start with a web browser in the left top corner, and the web browser, which is present on the user side, connects to our web application or web interface. That in turn connects to a login node through multiple different approaches like remote desktop or web terminal, demonstrated here. And there is a way to connect to the login node using a secure shell. Login node itself is connected to the computational infrastructure. There is a computational cluster. And there could be multiple of this, multiple clusters connected to the login node. They could be located in multiple different cloud providers, like Microsoft Azure, for example, and Amazon Web Services. And the web interface itself is also connected to the computational system through the database. And there is a direct way to access the database, which is through the RESTful API. So for today, we are going to speak mostly about these three: the secure shell connection, the remote desktop, and the web terminal. We'll speak a little bit about the folder structure and how the folder structure on the master, on the cluster, and the login node correspond to each other. And as you can see here, there is also something that we call Dropbox. That is essentially the same thing as people are used to these days as Dropbox, right? It's a folder that is present in all parts of the infrastructure, the login node, materials on the master, and on the compute node. We can store things like pseudopotentials and small scripts in Dropbox. Oops, excuse me. Okay, so remote connection methods, if you look at it in more details, they really contain, I apologize, keep on clicking it. They do have one thing in common, and that is all the remote connection methods, they connect remotely to the login node. And the login node is connected to the computational infrastructure through a resource management system, as demonstrated here in red. And there really are 4 different alternative connection methods. So the main connection method is through the web interface, and alternative connection methods are like this: secure shell, web-based command line terminal, which is equivalent to secure shell, but can be started from the web with no client needed. A remote desktop connection through a web browser to our login node again, providing CentOS Linux user interface and graphical tools like Vesta, Kristen, Nanolabo, and others. And the RESTful API that provides a programmatic means of communicating with entities through database. So for today, we'll speak mostly about the first 3. Here is an example of how we can set up the secure shell connection. First of all, we'll start with uploading the public and private key pair. So we upload the public key, we generate the public and private key pair locally. And we navigate to the account preferences, as I'm demonstrating here, to add a new key. Click on this plus button, and here is how it happens. So we click on the plus button, we call the key some human readable name, and then we choose the file from a local disk to import. As I'm demonstrating here, sorry, one moment. As I'm demonstrating here, there are two files, usually the public key and the private key, and we are uploading the public key. The private key never leaves the local system. So when it's done, you can see that the key is present, and when key is active, this LED here will turn green, and you'll see that you're able to connect to our infrastructure. The second option is the web terminal, which is essentially equivalent to a secure shell, but it doesn't need any client. It can be started from the web. And here's how I'm demonstrating. We open the right-hand sidebar and click on the terminal. And we are connected to our login node through a secure shell through command line. So here we can do things like upload a file. So all I did here is just drag and drop a file onto the web browser, and the file got copied. So I copied the SCF input file from my local disk to exabyte platform. And then when I want to download it, let's say here is the file. I'm demonstrating, also listing its content to make sure that it's consistent. So what happens when I'd like to download an edited version, for example? We edit the file, we change its name, and we would like to download it. For that, we have a tool as well. It's called exadownload. So these are specific tools that work with the web terminal for uploading and downloading files. So exadownload can download the file to local disk. Again, I typed exadownload, the name of the file, and I downloaded it to my local disk. Okay. One important note here is that the exchange of the files works only with the home folder. So you have to be moving the files from your current folder to the home folder before you can use exadownload to download them. Now, the third option is the remote desktop, which is a graphical interface environment, full desktop environment, that also can be opened in a similar way through the right-hand sidebar, as I'm demonstrating here. And when connected, you are presented with this view of the desktop. So this is a standard CentOS 7 GNOME desktop system. And users can use multiple applications within that environment. So some of them are listed here, like Expreston, Vesta, Turbomol, P4WASP, and others. So if there's something missing, you can contact us. We'll install it relatively easily. And of course, the graphical interface environment also includes tools like the command line terminal and file explorer and many others. Okay, so you can start the applications and visualize the data. Now, to be able to use the remote desktop efficiently, or any kind of command line connection, we have to understand how the remote login node file system is organized. So the login node is connected to multiple clusters, as I mentioned before. So in this picture, we assume that there's cluster 1, cluster 2, cluster 3. They could have different cloud providers or different cloud provider regions, different types of computational hardware. And all of them have a master node and computational nodes and storage. And what happens is that we aggregate the storage from all these different clusters on the login node, so users don't have to directly connect to all three. And the home folder to which user connects also have links to all these three different clusters, and they are attached or mounted on the login node under this absolute path. So all three connection methods that we discussed, SSH, Web Terminal, and Remote Desktop, connect to login node. And from there, we can navigate to any of the clusters. So this is what happens when we visualize the user home folder on the login node. There are multiple folders, just with regular desktop environment files. And there are two links to the cluster home folders, cluster 001, cluster 007. So when I navigate into one of these links, I am automatically taken to the home folder on the master node of the corresponding cluster. Excuse me. And here is how the home folder of the corresponding master node looks like. There are four important directories. The data directory is where the calculations that are originating from the web interface are stored. All the data that comes from the originates from the web interface. Dropbox we covered briefly. It's the folder that allows people to move data from web application to the computational infrastructure. exabyte.io is the name of the organization I am part of. And to quickly navigate to its data, there is also a link inside the home folder. And job script templates contains the script templates for command line jobs. Again, this is the Dropbox folder that we just covered. It is connected to the master node, to compute node, to login node, and to the web application as well. The data folder contains the jobs originated on the web interface, and they're organized in a particular fashion. So if the job is part of a certain project, let's say we are speaking about the username Steven, and Steven has a project named default, and he also named the job with the human readable name new job November 11, 2018 and such. So the job will be inside the data folder in such a slugified machine readable name, where it will include the username, the project name, the human readable job name in a compute-friendly format, computer-friendly. And at the end, there is also going to be an ID in a database. So this is how the jobs will be named in case people need to find them. The ID of the job is usually shown in the web interface as the last parameter of the URL. The organizational account have a similar data folder, but it's located under a share folder, not inside the home folder of the user. Now, why is it important to understand the infrastructure and how the files and folders work? It's important to understand it because we can have calculations that originate on the web interface that lack certain functionality. For example, we do not currently visualize Fermi surfaces on the web interface, but knowing how to navigate to the job files and opening the remote desktop session will allow us to use XKristen or Vesta to visualize this information. So here is an example, and it also is a link. Users can navigate to a tutorial that explains how to run a calculation for a Fermi surface and then visualize it using remote desktop and XKristen. Okay. So some summary notes about the remote connection. Remote connection is an alternative way to access the Exabyte platform. It can be enabled upon request. By default, it's disabled. There are three options: Web Terminal, Remote Desktop, both in browser, these two, and SSH session that requires a client on the user side. Remote sessions are connected to a login node with a separate home folder for each user. Home folder has links to directories for compute clusters as well. Command line jobs must be submitted from within a cluster directory, not within the login home directly. And there is a variety of different software packages available, both via remote desktop and via command line modules as well. Okay, so this concludes the first part of this presentation. It's time to ask whether we have any questions. If you do have questions, please raise a hand or type them in the chat. Okay, looks like no questions so far. So let's proceed forward with speaking about materials. So here, as we assumed in the very beginning, we will deal with a set of input files that users have already established. In this case, we'll speak about PWSCF, Quantum Espresso. And we will demonstrate how to create a new material in Materials Designer using parameters from the input file. So there are really two options as of how users can create new materials from PWSCF input. So the first option is like this. We would start with the input files. Here I have two input files, the SCF calculation and the NSCF, self-consistent field and non-self-consistent field calculation, that contain the same material information. This is just a workflow that was given to us by an example user. And what we do here is first we prepare the input files and open Materials Designer. So these are the input files that I have on my local disk. There's certain cell parameters. There's a set of coordinates, atomic positions, as you can see, in crystal coordinates. And the first thing I do here is I start open Materials Designer. Excuse me. And Materials Designer opens with the default material. In case of the webinar account that I'm using, it's the silicon. And since I don't want to work with it, what I do first is I clone it and prepare it. So this new material that I just cloned is going to be this material that I'm going to upload. It contains calcium, tungsten, and oxygen. So I'm renaming it ahead of time. Okay. So I have prepared this material. It's going to be like a stem cell that will be morphed into my material from PWSCF input. So the second step is to set up the crystal lattice parameters. And for that, I'm opening the crystal lattice dialog. And first, we need to understand what type of crystal lattice we have inside the SCF input file. There we had cell dimension 0, as you can see. So it's a triclinic lattice. We really are not specifying the lattice parameters. It's all specified by the cell parameters in here. So what I do there, I specify, I understand the lattice parameters, copy the lattice cell dimension number, and remembering that in Quantum Espresso it's in bores, I need to get it in angstroms, I convert it into angstroms. And I set it up as a lattice parameter for both lattice A and lattice B constants. And for lattice C, I would have to adjust it to a larger value. So I have to multiply it by the factor 2.15 coming from the input file. So I'm setting up the lattice parameters like this, A, B, and C. And then I also understand that the angles that I'm dealing with are all 90 degrees. That is evident from the input file. So here I have changed the lattice parameters for the material that I'm working with. Okay. Again, we started with the input file, Quantum Espresso. We took the lattice parameters from here, and we set them up inside the Materials Designer to create a certain crystal lattice. The third step is when we set up the crystal basis parameters. Just like we deal with crystal lattice, we can copy the crystal basis information from the input file as well. And as you can see here, the crystal basis information is presented in crystal coordinates. So we will need to match that with the user interface. We have it in crystal units already. And so I'm copying the information. Okay. And so now this is where my material is. I have copied the crystal lattice information, the crystal basis information. As you can see, crystal basis here also contains the the atomic constraints. In this case, there are no constraints, so they're all ones in quantum espresso XYZ format. By default, we add constraints to the material as well. So now you can see how this material looks like and make sure that that's what the original actually looks like. Okay, so the fourth step after we set up the crystal lattice and basis is to save this material. And for that, we invoke I do apologize. Just give me 1 second. Let's proceed a little bit further with this movie. So what happens is that we need to click on the input-output menu in the header and click on Save. And then since we imported this material from PWSCF input, it is handy to add a tag that will say that it was imported from PWSCF. And then we click OK to save this material. And when the indicator in the top corner shows us that everything went successful, we know that material was saved. So we can exit Materials Designer, come back to the list of materials, and see this calcium, tungsten, oxygen 4 imported from PWSCF present inside our list of materials. So this is how we create a material from PWSCF input. Okay. The second option is to first convert PWSCF input to POSCAR using external resources. We do not support a direct conversion as of right now. And then upload POSCAR information. That we covered already 2 weeks ago in the Getting Started. And once you receive this presentation, you can click on this link and understand how to do that. But here I'm highlighting a web page that is handy to convert between different formats. So OpenBabel is an application that can be installed on any Unix or Mac environment. And it can convert from PWSCF format to POSCAR. So if you copy paste the content of the file here, you'll get the POSCAR and that you can further upload into your platform. So this is an alternative way, and many other formats can also be uploaded by converting them to POSCAR in a similar way. Okay. So I think I'm mostly done with the second part of this presentation. Are there any questions at this point? Okay, looks like no questions yet. So we'll proceed to workflows. Again, we will have the same exact problem that we will deal with. We are an established computational material sciences. They have these two input files and certain way to execute a calculation. I'd like to understand how to migrate this workflow to the exabyte platform. So first step in doing so is to prepare the input files and open the Workflow Designer. And these are my input files, SCF input and SCF input, just like in the previous section with materials. And I start with navigating to the workflows list in the user interface and clicking Create to create a new workflow. It opens the Workflow Designer, and I am presented with a new empty, at this moment, workflow that contains one new subworkflow. So my second step is to edit this empty subworkflow, adjust the name of the workflow, new workflow from PWSCF input, and I call the subworkflow SCF and SCF. So it will contain two units, SCF and NSCF. Okay, all the other parameters are the same. Now, the third step is to add a unit to a workflow and make sure that all the parameters are according to what I want them to be. And navigate to the units panel and click on plus button here. So I select the execution unit. PWSCF units are execution type. They don't have any logic. They just have the execution part running pw.x. And here we go. I have added PWSCF unit. This is the default unit type that is being added. Now the next step is to navigate into this unit to adjust its content. Step number 4, edit the content of the unit template according to original PWSCF input. So I click on the name of the unit, and as you can see, there are multiple predefined flavors that we have created that include PWSCF, NSCF, which will be handy in just a couple of minutes, bands, relax, VC relax, all different types of calculations that are present for pw.x input. We have pre-created as a template flavor. So users can quickly navigate between them and get the templates according to the type of calculations they want to run. Then there are other parameters like properties that we'd like to extract. I'll just keep them as default for now, the monitors as well, post processors, and I'm going to go directly to the template input. At the bottom of the page, we can see the template input. And right now it contains certain set of flags that might not be exactly the same as I have inside the input files on my local disk. So I'm looking back at the input files and I'm comparing, understanding which flags are missing. So there are certain flags like lk point directory, disk.io, and verbosity that are not quite the same in the template presently as they are in the input file. So I'm copying them and directly editing them inside the template editor. Okay, now I'm going through system part, and I think there is something missing there too, which is the type of smearing. I'm explicitly setting it to Gaussian. And then under the electrons name list, there are certain other parameters that were present that are substituted by default. So I'm copying them as well and removing the originals. Okay, so I'm matching the two files, making sure that they all contain the same information, removing extra name lists. And when it comes to atomic species, atomic positions, and key points, I'm not changing anything because these are going to be set by default based on material information. Again, here in the input file, we always deal with a single material. In the template, we can feed material data and construct material information like atomic species on the fly. So I'm keeping this information the way that it was originally. Now, if I'd like to understand how the template will be rendered with some example materials data, I can use the default material. As we can see here, the default material is silicon, and see how the template is going to be rendered. There are some variables that will still be present and that will be rendered on the computational infrastructure. Like on the web browser, we don't really know what the job working directory is going to be. It's going to be decided upon the submission. So when the job arrives to the computational infrastructure, this variable will be substituted there. On the web interface, we substitute the other information, like the number of atoms, the number of atom types, wave function cutoff, the density cutoff, charge density cutoff, based on the workflow parameters and the material information. So again, we had variables like this in here that were substituted using the information from material. So here's how the rendered template is going to look like, just checking. This is the first unit, and now we repeat the same procedure for the second unit. So the first unit was the self-consistent calculation. The second unit represents the non-self-consistent calculation. Again, we are adding another unit by default. It's PWSCF. We're changing its type right now to NSCF to have a helpful template with a calculation type here. And again, just like in the previous case, I'm copying all the parameters that I'm missing and setting them up. Okay? Exactly the same procedure. So at the end, when I'm done, I have a workflow with a single sub workflow and 2 units, PWSCF and PWNSCF, as we can see here. So now it's time to rename this workflow, SCF and SCF, add a tag to it to understand in the future that it came from PWSCF input, and save it. So we click on the Save button and the check mark here in the top right corner, and the workflow is being saved. When the workflow is saved, we can see it in the list of workflows. So here is the workflow that contains templated language that can be applied to multiple materials that was derived from PWSCF input. Okay, so again, we're navigating back to the workflow, just checking that everything is fine, which it is. All right, so here we have the workflow created from PWSCF input. Now, another way to accomplish the same would be to, instead of starting with a completely empty workflow, we could start with a bank workflow that does a similar calculation. Here, I'm just demonstrating to you how a user can copy a workflow from a bank. So we can navigate to the workflows bank that contains all unique workflows created in the system, in the platform. So we can open the left-hand sidebar, navigate to the list of workflows, and search for band structure calculation. As you can see, there are multiple other people, including the exabyte team itself, that have created workflows that do similar calculations. So they do band structure calculation in this case. So what we can do is we can select one of them and copy to a private account. So in this case, the band structure plus density of states workflow will be copied. And then instead of starting with an empty workflow, we can start with this workflow that already contains the required logic. Okay, just give me one moment here. Okay, the ambulance has passed now. So let's continue onwards. So these are the 2 ways that users can create workflows from PWSCF input, either starting from the default empty workflows or starting from the workflows copied from bank workflows. Do we have any questions at this point? Okay, no questions, no hands raised, so we'll continue on to the jobs. Okay, so now we've arrived to where we originally started. There are 2 options for migrating the established workflows, so the established way that computational material scientists are dealing with their tasks, to exabyte. The first one is to bypass the web interface and use alternative connection options. And we will name it as CLI for now, command line interface, short for command line interface. And the second option is to use the exabyte platform approach and migrate materials and workflows that we just did and create a job with this new materials and workflows. And we will call this UI. So there are 2 types of jobs, jobs CLI created in command line and jobs UI created in the user interface. We'll cover the first one first. So to understand how we can create a command line jobs, we need to come back to the user home folder on the cluster. And remember that there is a folder called job script templates, a subfolder under user home. That subfolder contains example job scripts that can be quickly copied and reused. So really there are 2 ways to create a new command line job. And I'm putting links here so users can follow these links and read the tutorial information. The first one is to use the JavaScript templates folder to quickly set up and run template calculations. And the second one is to use and modify a template JavaScript to create and run a command line job. So this is the option that we're going to be using right now. We'll start with a template JavaScript, and we'll prepare all the required information for the command line job to run. Again, we are starting from PWSCF input and are executing a command line job here. So calcium, tungsten, oxygen 4. We have the two files, SCF and SCF, and we are opening this tutorial that we are going to be following for the purpose of this video. So this is the tutorial available on the documentation online, how to create and run a command line job. So the first thing I have to do here is I need to open a command line terminal, Web Terminal. And inside the Web Terminal, I first list it, and I see that I have links to cluster 001 and 007. I also have other clusters that are no longer present in the platform, but other users will not have them. So we should only have cluster number 1 and cluster number 7. And I'm going to run the job under cluster number 1. So first thing that I do is I navigate into that cluster. cd cluster -001. Then I list the home directory of that cluster, and it contains multiple subfolders. Now, since I am a member of multiple accounts, there are multiple account directories that are also listed here. I'd like to run my calculation under the seminar account. So the next thing that I'm doing here is I'm going and changing my directory into the seminar account. So I navigate into the seminar account directory under cluster 001. Okay, so now there are some other project-related directories present here. I'd like to create a new one, so I'm creating a calcium tungsten 04, CAW04. It's a directory where I will execute this command line job, and then I navigate into that directory to start preparing my files. Next, I copy the input files from my local disk, this SCF and NSCF input files. All I need to do is just to drag and drop them into the web browser. So this is exactly what I'm doing. So you can see there are NSCF and SCF files that I copied. And they are by default copied into my home folder on the login node. So I need to move all these files into my current folder, which is what I'm doing. So I'm moving all the files that start with calcium tungsten 04 into my present folder. And you see there is also the edited file that I'm removing. I don't need it anymore. Okay, so I have prepared the runtime directory, copied the input files. The next thing I need to do is to prepare and copy the default pseudopotentials to the runtime folder. I can also upload pseudopotentials from disk here, but I'm choosing to use the default set that uses GPRV pseudopotentials. They're pretty good for the purpose, so I'm just continuing to use them for this calculation. As you can see, the input file already contains certain pseudopotentials that are not present in the current runtime directory, so we'll have to adjust those. All the other parameters will keep the way they were. So now what I can do is I can copy the location. The location of the pseudopotentials are under the /export share pseudo directory. And that contains pseudopotentials arranged by the chemical element. So depending on the chemical element, the location will be different. There is also a set of subfolders that denote the model and method that are functional, that are used for this particular pseudopotentials, and its type. So what I need to do is I need to copy and paste this file path into my web terminal. And for that, I have to open this sidebar. To open the sidebar, I'm pressing Control-Shift-Command. So 3 keys. open the sidebar and copy paste the location of the folder. Okay, so now instead of silicon, I need calcium, tungsten, and oxygen. So first I'm copying the calcium to the potential, like this. And then I'm copying tungsten to the potential, oxygen, and tungsten. So now I have all three of them present inside my runtime directory. The next step is to adjust the input files to use the input files that we have here inside the runtime directory instead of the original ones, which is exactly what I'm doing. I'm adjusting the STF first and then copying that information into the NSCF file too. Okay. So by the end of step number 3, I have all the necessary files to be able to run the calculation except for the job script itself. So to prepare the batch script for the job, what I need to do is I need to copy the content that is given to me inside the tutorial and upload this content to the command line. Now I adjust the input files according to what I have in the directory. I'm just using SCF input and SCF output. And I'm also using a trick here where I pipe the calculation into a T command. Using T command will allow us to see the output of the calculation in the real time in the web application. So instead of just piping it to the file, I'm using T to be able to interactively see the output in the real time as well. So, okay, now I'm moving the output files to have shorter names. And now the last step that I need to do is I need to introduce the logic from the calculation into my job script. So the logic is relatively simple in this case. I'm just running 2 calculations in succession. So scf.input and nscf.input given to pw.x as executable. There are some parameters here that we're going to need to adjust as well, like the project name and the email. The email is easy. I'm just going to change it to my timur.exabyte.io email. I'm also going to change the name of this calculation and adjust the computational parameters. I'm not going to use 16 cores. I'm just going to use 1 core for now. And I'll submit it to the debug queue to make it start faster. Now, to understand what to put inside the project field, I need to come back to the web interface and see which projects I have. I'm using the webinar account, and the accounting name for the webinar account default project is like this, seminar-default. And that's the exact phrase that I have to use inside the job script. Okay, so I'm navigating back to the folder and substituting the project with that phrase, seminar-default. What happens then is that the accounting system will understand that for this calculation, it will have to charge the account whose name is seminar. That's the account that we're using. It's a name in the infrastructure. And it will be charged to the default project of that account. Okay, so the next step is for me to submit the job. I'm using qsub and qstop to understand the status. We can see that the job starts running relatively quickly. And now what happens is that the job itself, the file that I'm calculating here, is relatively large. It contains 24 items. So obviously running it on a single core takes quite some time. So to speed up and demonstrate how this calculation can be done, what I'm doing is that I'm adjusting the cutoff parameters to make it run faster and adjusting the key grids. So you should not do that in a production calculation. I'm just doing it to demonstrate. So I did that and I have resubmitted the job again. So now we have 2 calculations submitted. One of them is for the production type, K-grid and production type calculation. The other one is just a quick example that I have created. Now, if I'd like to delete one of them, which I'd like to right now, I'm going to need to delete the job by its full job ID. So I'm copying the job ID here, which starts with 68951, .master production, etc. So I'm passing that to QDEL, and it will help me to delete the job, which I'm confirming with QStat again. So now I have a calculation that I can track, and I'm using tail F to see the progress, and I'm tailing the scf.out file. So here we can see the SCF calculation already finished, and then NSCF calculation already finished too. And within some time, I see that my calculation is completely done. Okay, so the SCF and NSCF files are both present, the output files for them, SCF out and SCF out. There is a file that contains the system output, the resource manager system output. And there is also .exabyte folder that contains some system files too. Now, after we're done with this calculation, there is also one more step that we can take optionally, and that is to view the results on the web interface. By default, we attempt to parse the command line calculations and we post them to the web interface. So although we run a job in command line, there is also a corresponding job created on the command line with the corresponding name. And we can see that it's already finished. We can navigate into it and see the results. Some of the results that we have attempted to extract in its files. Now, when I mentioned that you would be able to see the output files in the real time, that is possible on this workflow tab. If we navigate further down and open the unit, we will be able to see the unit output in real time as the job was executed. Now, the seventh step, which is also optional, if I'd like to, from the web application, I can share this job with another account. So here I am a member of my personal account, Timur Bashirov, as well as the organizational account for webinar. And now I'd like to share this job with my personal account, which I can do using this dialog. So I'm selecting my account here and giving it the read permission. So here is how I execute the command line job and share it with my personal account in the web application. Now, the second option, as we discussed, that's what we have just covered, was the command line option. So we are bypassing completely the user interface except for the last two optional steps. This jobs UI option, instead of bypassing the user interface, actually uses the platform to create a job from the PWSCF input and material and workflow that we previously covered. So these two steps, 1 and 2, are already covered. Step 3 would be to create a job and select material and workflow inside it. So to create a job, I navigate to the jobs list and click on the plus button. I navigate to the project first and click on the plus button to create a job there. And I'm naming it CAW04 job SCF and SCF. And I'm selecting a material for this job, which is calcium tungsten 04 from PWSCF that I have just created. As we can see, material is exactly as we created this. And I'm selecting a workflow for it. Again, this is the workflow that we have just created, SCF and SCF workflow from PWSCF input. So the first two steps is to select material and workflow according to what we have just created. Step number 4 is to inspect the workflow and adjust the unit input file parameters as necessary. If we remember it correctly, the handy feature here is that the pseudopotential information will be substituted automatically, so we don't have to adjust that. If you remember it correctly, the key-point grids that are present by default are not quite the same than the grids that we used in the original input files. So we had 5 by 5 by default, and there is 4 for 2, 8, 8, 6 in the original input files. So what we do is we navigate back to the important settings of the job, and then we change the key grids inside the important settings to 4 by 4 by 4 and 8 by 8 by 8. just like this. Okay, and now this will be reflected inside the input files too. We add edited K-grid into the name of the job. The next step is to set up compute parameters, which we are going to just use a single calculation node. Since this is a large calculation, I'm using the ordinary regular queue, and I'm using 18 cores, half of all the cores available, and I'm selecting notifications, so I will receive the notifications about the completion and the beginning of this job. And next, I'm saving this job. So clicking on the save button at the top. All right. And when the saving proceeds, I can see that the job has been created inside the project that I'm looking at. I'm selecting the actions available for this job inside the dropdown and clicking on run to run. Next, what happens is that the job goes through multiple different statuses. So right now it is submitted. It takes some time for the infrastructure to be provisioned. I'm speeding up this calculation. So within 2 minutes, as you can see, the job gets into the active status. I'm speeding up the video, but this was a production run that I executed just yesterday. So it took 2 minutes for the infrastructure to provision the resources in the cloud. And then within a couple of minutes, you can see we can track the progress, the convergence, the input files for the SCF and NSCF calculation as the calculation proceeds. And when the calculation is done, there are 72 K points. It takes about 15 minutes or so. When the calculation is done, we can see that both of these units are colored green. So PWSCF, PWSCF are finished. So we can view the results. For that, we navigate back up to the top, and we can see that together with the materials, workflow, and compute tabs, now for the finished job, we have the results and files. So if we navigate to the results tab, we will be able to see the results of this job for the properties that we originally indicated to be extracted in the workflow. And in the files tab, we can see all the files that correspond to this calculation. Okay, so here is how we can run a calculation, a job, from PWSCF input on the exabyte platform without needing to use command line interface, just using the web interface. Now, here is the final notes that I have in comparing the command line jobs and user interface originated jobs. CLI jobs are quick to start with and can be familiar to many already, but they require users to modify and edit the input files each time when a new job is created. This is prone to error, and although familiar, this is something that is not that great, because it would be good to have some ways to reuse the logic that is present in the job without having to modify the files, right? And that is exactly what the UI jobs provide. They take time to get used to initially, but when implemented properly with a flexible workflow unit templates logic that I just demonstrated, they can be easily created for large sets of materials at once. Most of the people use a limited number of workflows, so they deal with maybe 5, 10 different types of calculations usually. So once the workflows are migrated, there is little modifications that need to be done to those. And this is the advantage of using the user interface. And there are also certain other advanced parameters like spanning other jobs and waiting for their execution that can be done using the UI jobs as well, but we'll cover them in a separate advanced topics webinar. Okay, so I think I'm coming down to my last questions and answer session. We are 2 minutes past the 8:30 time mark. So do we have any questions at this point? Anything that wasn't clear? Okay, looks like no questions still. So I will make this presentation available to all the participants. Again, you will receive an email with a link to the PDF that you can follow on your own time. And you will also receive the video recording of this presentation, so you can follow it along on your own time. If there are no other questions, we will conclude this webinar at this point. Thanks everybody for your participation, and see you again in 2 weeks in our monthly series and the Getting Started webinar. Thank you.